My name is Sheldon Cohen. Today, along with two of my colleagues, we'll be presenting to you some of the new features of OSATE that will soon be incorporated into the standard release. These provide better and improved capabilities for performing some of the analysis currently built in, but they have been revised and updated in order to provide better user input. This set of demonstrations will focus on a number of resource analysis that OSATE can perform. And in fact, they are currently performed as analyses within the current version of OSATE. During the class this week, you have probably executed some of these analyses on the models as you were building them. What we're going to demonstrate today is a different user interface that provides a little bit more flexibility in setting up the analysis and also provides more user input to the analysis, review, and revision process. When we say resource analysis, we're talking about a set of analyses that can be performed based on property values that have been assigned to an AADL model. The units of measure that are used in measuring these properties are not defined in the AADL language itself, but are part of the plugin resources. And you've been using many of these resources out of the package SEI AADL. The property set includes several values that we'll actually be illustrating with our analyses today, including processor capacity, RAM, ROM, in terms of memory, also processor speed units. We'll also have power budget and other power units, data rate for bandwidth, and several other types of measurement capabilities that come about through the SEI property set. This table is built to illustrate the way in which certain of these resources correspond to specific categories of components. In particular, we'll be doing a weight analysis, and in this example, weight limit as a property can be applied to a number of different types of components, system, processor, memory, bus, and so on. The net weight or gross weight, which are the individual weights that, when added together, have to come in less than the weight limit, according to the weight constraints, are based on really the same set of components. So for the analysis, a system may have a net weight, and that system may be part of a larger system that has a weight limit. In addition, there may be components such as memory or a device that have net weight or gross weight, and the sum of all of those individual components, when added together, should be less than the weight limit in order to meet the weight constraint. The similar capabilities apply to the other resources, and we'll cover those in a little bit more depth when we get to the analysis. One of the things about the weight analysis that makes it a little different from the others is that weight is kind of an intrinsic property. A device has weight, a bus has weight, certain other systems have weight, and they can be added together and measured against the weight limit. But when it comes to some of the other resources, it's necessary to attach the component having that particular resource demand to a specific reference processor or reference bus. When you do that, you establish certain types of connections, and those connections are necessary in order to actually do an analysis. For example, if you think about it, when you do the electrical power analysis, if nothing is plugged in, no power is going to be drawn from the power source, even though when running, a sensor may draw a certain number of watts or the processor may draw a certain number of watts. Similarly, if a data item is transferred back and forth between memory, it's going to require a certain amount of memory budget, and those budgets together will add up to memory capacity. But if there is no data flowing back and forth between memory and the processing capability that needs that data, then there's zero memory being consumed. So we'll cover those individually as we go through each of these analyses to explain how certain additional properties are necessary in order to complete the analysis. Previously, you were looking at a diagram of an AADL model that I called the central control system. What you're looking at right now is the actual AADL itself from which that diagram was created. What we can do by going through this in a very quick fashion is to look at some of the highlights that showed up in that particular diagram. So if you recall, I said there was a high-level system called SCS, and if we look down here through the code, you'll find an SCS system defined along with various implementations, various forms of that implementation. The SCS system itself has some properties that we've assigned to it, and one in particular is a weight limit. So the first analysis that I'm going to run will actually illustrate the weight limit and determine whether the individual elements within the SCS conform or meet the constraint of this particular weight limit. In order to talk about the individual components, I need to look at an implementation of the SCS system, and that's shown immediately below here, the SCS implementation, SCS Tier 0. So I said before when we were looking at the diagram, the sensor control system consisted of a number of subcomponents. One of them is the digital control system. Another is the sensors that are part of the system and the actuator. When we looked at the diagram, there was one sensor, but in this particular implementation, there will actually be two sensors, each of them of the device sensor type. The other implementations of SCS expanded along with the different versions of DCS or DCS implementations that are built above in the AADL model. So if we go back up a little bit, you'll see DCS, Digital Control System, and you'll see here that the digital control system has a number of features. Among these are the access to the CAN bus and sensor ports and an actuator port. The implementation of DCS itself has a software app, DCA, which showed up in the diagram, Digital Control Application, as well as hardware, which is the system platform. And I need to go up a little bit higher to see what those are all about. So if I go up here, I'll see that the platform itself consists of platform implementation that has a CPU processor, PowerPC processor, main memory, and a CAN bus, and a dual processor capability with two PowerPCs. Here are the sensors and actuators. They have weight. It'll play a role in the weight calculations and determining whether we're going to meet the weight budget or not. And then if we go up just a little bit more into the model, we'll actually start to see some of the software capabilities that are built into DCA. That's the digital control application. It has two processes. Those processes are elsewhere located within this AADL model. So in order to actually run any of these analyses, you need to create an instance. And for the purposes of today's review, I'll recreate an instance that actually shows up over to the left, and that's the SCS Tier 2. Instantiate that system. You'll see here to the left, Tier 2 instance, and I can actually view the fact that that instance includes a power port, it includes the two sensors that I mentioned, includes the actuator, and a system instance for DCS. Now, it's probably worthwhile, just to get a better feel for this, to look at the actual instance model itself and to expand some of these elements to look at the property values, because we're going to be running an analysis on them. There's the weight property, DCS as the hardware that's associated with some of these hardware devices. And the actual overall weight limit is defined here as 1.2 kilograms. So what I want to be able to do now is run an analysis of the weight, and you probably did this in your class already, but I just want to illustrate how that works in the current model, current version of AADL. Nothing visible on the screen, but if I check reports, I'll see that I did generate a weight analysis. If I grab that, I'll get some information about it. Here are the two sensors and their weights. There's the actuator and its weight. Here are some devices that may or may not have weight. And finally, the sum of weights, 0.66 kilograms, is below the weight limit of 1.2 kilograms. And in fact, there's some amount of slack that's shown here. So that's the way in which the current analyses are run.
You've seen examples of resource analysis during the course, and I demonstrated the weight analysis in the existing AADL toolset. And I'd now like to show you the new workflow method that we're developing that will be incorporated into the standard AADL toolset. The example that I'm going to be using is the same example that I used for the current analysis. I'm going to go back and instantiate that system, and we'll be using the tier 2 example, but this time I'm going to be using the dual tier. If we look at the dual tier, it's based on DCS dual tier, and in that particular example the main difference is that the DCS dual tier includes a dual platform, platform.dual. The distinguishing feature there in platform.dual is that it has not one but two PowerPCs. However, because of the way that I've set up PowerPC, I go back to the definition. PowerPC currently has no weight, at least it has no weight assigned to it. So when I actually ran the analysis in the previous example, you had weights for the two sensors and the actuator, but for none of the other devices in the system, which really isn't a realistic model. What I want to do now to explore the new workflow toolset is to get an understanding of how to do some updates to that current model, and to show exactly how we can modify the information in the model to present a more meaningful type of analysis. So the current version of the tool, kind of the current testing version, we go to Show View, and there's some special analyses that are present there. They aren't present in the current AADL release, but only in this test release. And I'm going to select weight workflow. And the weight workflow gives us a selection of instance model. In this case, that's pointing to tier 2. I want to update that to dual tier 2. But if I go to the weight limit and some of the other information, you'll see it's currently in the same state as the previous example. There are weights on each of the two device sensors, on the actuator, but the processor PC weight, processor PC memory, and other devices don't have any weight attached to them. Now that's the power of the new workflow example. that one of the activities that this allows is resetting, or in this case setting, the gross weights for some of these devices. So if I run the analysis right now through the new tool, I'll generate the weight analysis report for dual tier, and exactly the same as I had for the single tier example. Go back and now I can delete that so that I can update it and rerun it. So what I want to do now is to look at the weight contributions in this table, and I can set new weights. I don't have to go back to the code directly. I can indirectly, through the instance model, change these weights through the tool and apply some values here. So I'll plug in 0.1 kilograms there, and I've got two processors. Let's say each of them weighs 0.4 kilograms, and another one's 0.4 kilograms. And you'll see that those weights have been added as new properties to the instance, to the implementation, and we'll update the instance as well. If I go back to the declarations for those devices, get them here, those haven't changed. It's only the instance information for the implementation where the actual weights have been changed. So I can, in theory, if I want to, delete these properties, revert back to the original, and I haven't really made any changes to my original definition. So this is pretty much a tool to be used to do some exploration. In this case, it's exploration of changes in the weight assignments. In the other tools, it can be changes in power or throughput assignments, whichever resource you're examining. Now, if I run the weight report again, I see that because of the changes that I've added, these three new weight amounts, added 0.9 kilograms to the total, that my sum of weights now exceeds the weight limit. So we have an error state. So I discover now the fact that I need to go back and make some adjustments in my design. If I'm still operating under the weight limit, I would need to find some improved devices, improve the weight or reduce the weight of the devices, reduce the weight of the I have that open still, reduce the weight of the devices or reduce the weight of the memory, and then I can get myself back under the weight limit. So I'm going to attempt to do that now. So I'll look at my weight contributions and I'll say, well, I need to cut back in some areas, so maybe I can go out to a manufacturer and find a lower weight sensor, lower weight actuator here. Probably can't do much with the sensor devices, but maybe I have to, if I'm going to do a dual processor, I have to find processors that maybe aren't as capable, but will allow me to stay within my weight budget. And that might mean compromising on processor capabilities, but for whatever reason I need a dual processor configuration. And I'll store those amounts, rerun the weight report, and I'm barely under the limit as shown. So that gives you an example of how we can run the weight analysis and to be able to use the weight flow workflow example, workflow tools to update, change make some adjustments and return back to an under budget situation.
The next example that I'd like to illustrate is power analysis. Power analysis takes a look at the power sources and power capacity from various elements in the system and compares those with the power budget. Those are, again, our systems or components that draw power from the power supply and the power capacity. In the example that we looked at already, the resource budgets, there are a number of devices that rely on power to the system. And when we go through the AADL, we'll find a couple of those here. For example, the Power PC has a power budget of 0.8 watts. CAN bus, 0.8 watts. Main memory, 0.8 watts, and so on. And in addition, there is a power budget across SCS of 2.5 watts. First, I'll run the analysis as it's currently built into AADL. So in order to do that, I'm going to instantiate my system implementation, SCS Tier 2. I actually have that already, but I'll do that again just for illustrating the process. So I create that instance. It's right here. Check just to make sure it's correct, which it is. And now I'll run the built-in analysis on that model. Analyze power requirements. Some message of some kind showed up there. Not quite sure what that is. Let me look at the report. And I got a big blank. So what I need to do is, well, look at the code, see what's going wrong, see what's happening. Everything looks okay. I've got power, got a power source. But if you look a little bit closer, you'll see in the instance model that something of vital importance is missing. Now up in the instance model, and you'll see some of the power budget information. That's contained as property values, but you don't see any connections. It's like you had the devices sitting there, but nothing was connected in. What I want to do now is to illustrate an example where I actually have created some of those connections. So this one is called Power Test 2, and I went through the resource budgets and added some ports, connected those ports up so that there's now power flowing through the system. It's not just static items sitting there that have the potential to draw power, but they're actually plugged in and power can flow from supplies to the individual devices. So for example, you'll see here bus access from the Power PC to the power supply, and it has a power budget that's going to be drawn through that bus access, assuming that power is run on a power bus. There are other ways of accomplishing this in AADL. The illustration of the resource budgets is not going to illustrate all the various mechanisms within AADL that allow that, but we'll make the software code available, the AADL available to you, and you can go through there and see the example. So another one is that the platform also has power access, as it says there, requires bus access power supply. So now I'm going to illustrate running the power test in the analysis in both the original analysis format as well as in the new workflow analysis format. The first example will be an example that won't really generate a report. It's power test 0. As we pointed out before, there's no connections, so everything's unplugged. So I'll reinstantiate power test 0 and just to run the analysis and show you what happens. You don't get any feedback. You don't get any illustration of what's happening. You just get a report that's blank. At least when I do run the power test in the workflow, let me get that started here. Power workflow. I select the instance model, which is power test 0, tier 0 instance. So if I look at the power connections, I see connections, but none of them have power supply, capacity, budget, anything real going on there. So even though I don't have power budgets either, so I don't have any real values to deal with in this particular example. If I run the power analysis report, I'll get the exact same results. So now let me try running power test 2. In power test 2, if you look at the AADL for power test 2, you will see that the connections are present so that power is going along a bus. And again, tier 0 as electrical to DCS, bus access, electrical to DCS power. So power comes into the DCS, and with that, you're able to generate a report. So let's go ahead and I'll instantiate this particular implementation, which is power test 2, SCS tier 0 instance. And if I run the analysis here, I actually get some numbers. So I get a capacity, I get a supply, I get a budget. For DCS, because I showed the DCS was connected, and everything is based on the amount of information, the amount of connections I've made, as well as the electrical power for each. But if I do the power analysis using the workflow, let me set that one up. That's going to be power test 2. If I see the electrical to DCS power as 2.0 watts with 100 watts of the power budget. See devices there with a power budget, and so on. So I'm getting some meaningful results. Now the last example in the power test case, I set up to be able to illustrate parallel power supplies, or multiple power supplies I should say. And in that particular case, there's power from the electrical power bus. There's power from an abstract, undefined exactly what that means, but maybe an auxiliary power unit. And there's also the actuator sending power into the power grid by some mechanism. At this point of the design, we don't know exactly how that's happening, but we wanted to be able to say that there is a device there that's putting power into the overall power grid of the system. And now I'll do the instance of tier 0 again. and then it's power test 5. And I'll run the electrical analysis on that and show you that the numbers come up. I don't quite know how to interpret them without going back to the code. And so that's the power of the new form of these models, because then I actually see when I run power flow with the current instance model, that's power test 5, I can actually view the connections and see which connections are present, the power supply in each connection, power capacity, power budget, and so on are working properly. And I have one more little piece that I wanted to illustrate, and that's if you want to do something that's going to potentially change a value. Can't do it in the, I can't do it in the connections. I can only do it in the actual illustration here. The connections view does not have full access to the values in the instance model, but we do have access to them here, and I can go into the power workflow and say I want to increase that power supply coming from the actuator. Again, the actuator is some kind of a device that supplies power into the power grid. It's not the bus itself, and it's not the auxiliary power unit that is supplying power. As power sources, power capacity, it's a power supply. And I can now run that, and the screen sort of shifts there, but this is the value now at 4.8. So now if I want to check out my power supply value, it comes back as 4.8. And that's useful because if you've done a model and you want to sort of do some analysis, what if I increase power supply or some other property in mid-analysis? I can do that without having to go into the AADL model, find the value, update the value, make sure I've got the right location and so on. The workflow shows you in a tabular position dependent way where power is or where bandwidth is or where other properties are, and you can easily adjust those for rerunning the case, rerunning your analysis case. Good. Okay, so now that I've completed that, if I want to, I can go back and reinstantiate it because the instance model still has to be updated. So now I'll reinstantiate this implementation according to my plan. And it looks like it's ready. And I'll run the power analysis on a reinstantiated version just to make sure it's reconnected in. And we should see here, once again, the new value of 4.8 watts for the device actuator power supply. So that completes the demonstration of most of the features that are going to be installed into OSATE. I think just to summarize, under the old initial version, you created your model. You could kind of view the instance and go searching through to find the individual values of interest, and then run an analysis that may or may not produce results. The new version allows you to select the appropriate instance model from a specific menu, and once you've selected the instance model, it can factor out the individual items for viewing their particular properties based on the type of resource values, power supply, power capacity, and power budgets in this particular case. And in addition, since connections are of significance in the power budget analysis, we can also view those connections that carry power on them to make sure that the system is hooked up properly. When I run power analysis report, I get the exact same report as I did before, but I have a better sense of where values come from and what numbers and so on will appear in each value of the property table. And finally, I can do one more thing that I cannot do in the original version, which is to go into the property tables, update values, have those reflected back in the AADL model, reinstantiate, rerun the analysis to perform those what-if analysis kinds of studies. So if I add a little power here, take a little power there, am I now back in budget?